Last time we looked at chi-squared goodness of fit. This distribution tested whether or not a claimed distribution, some p1 up to pn, was a reasonable fit to our sample data or not. The alternative hypothesis is that at least one of those values is different. The way we found this chi-squared number was we started with the percentage error by doing observed minus expected over expected. We saw that we had sign errors where positives and negatives were canceling out when we added them. Reminder, this symbol means add. So I squared those numerators of the individual values to deal with any sign issues along the way. When I'm talking about the expected value, it's the number of total trials times individual probabilities. There are 4 assumptions for using this model. Random, sample, I want to make sure there are no biases. Independence between trials, one trial does not affect another. I have a large enough sample size that my curve starts to smooth out. And finally, I have data that I can count. My chi-squared curve looks something like this. The degree of freedom is always k minus 1, where k is the number of categories. The smallest my chi-squared can ever be is 0. The mound happens at degree of freedom minus 2. And I start wherever my chi-squared is, that or more shaded to the right. So when I'm looking this thing up in my calculator, I would do something like second vars on a TI-83 or 84, for example. I have chi-squared CDF, whatever I calculate using this above calculation, comma infinity, comma my degrees of freedom. Fourth step of a hypothesis test is always a conclusion. I determine if an individual category is off using these things called standardized residuals, and I'm thinking z-scores when I do so. Let's look at an example of this thing from start to finish with a smaller set going on. So according to Marvel Comics, 10% of all Miss Marvel covers are considered variants. If 200 Miss Marvel comics are sampled and 15 variant covers are found, what can we say about Marvel's claim for the distribution? So this is not the only way to do this problem. In fact, we used to do these types of problems using 1 proportion z test. So for those of you that are curious about what the results for the 1 proportion z test looked like, for the null hypothesis for that test, it was claimed that 10% were the special cover. Alternative, I'm testing if it is different than being claimed. If you go through and calculate the z-score, I get a z-score of something like negative 1.1785 or so. And this gave me a p-value of 0.2386 or so. And I would encourage you to try to go through this process again using this p-hat model that we had from a much, much earlier lesson in the term. Now I'm going to be looking at exactly the same data set, but I just want to use a different distribution to show you sort of what your options look like and to also just practice chi-squared a bit more. So for the null hypothesis this time, I have the percentage of variant covers that's being claimed should be 10%. That's matching up with our old way just fine. An alternative, I also have non-variant covers as 90%. Alternative is at least 1 proportion is different. If I only have 2 proportions, if one of them is wrong, then both of them end up being wrong here. So this ends up being entirely equivalent to the previous set of hypotheses, but I'm just setting this up the same way that I would for any chi-squared, where I have each of those individual probabilities that are being claimed. So let's look at the second step. And when I'm doing the second step, I personally find it helpful coming up with the model to make a small table with what the observed values are, what the expected values are for both the variant covers and the non-variant covers. We observed 15 out of 200 that were these variants out of 200. So that must tell me that I can solve for this missing one, even though they only gave me 1 piece of information. So my degree of freedom, if I knew one of these two columns, I could solve for the other values. So my degree of freedom is 1 for this problem. 15 removed from 200, I believe, leaves me with 185 for the number of non-variant covers. Likewise, if I wanted to figure out the expected number, well, I was expecting 10% of the 200 to be variance based off of the claim for Marvel. So I really should have gotten about 20. Looks like I'm off by about 5 for that category. This is still out of 200. I could do 200 times 0.9 here to figure out this other value. But just a quick note, I could do subtraction as well, because 200 take away 20 leaves me with 180. And that's exactly the same thing that I would get if I did 200 times 0.9. I want to calculate what my chi-squared is so I can find that p-value. So I'm going to do chi-squared is equal to observed minus expected squared over expected for the variant covers. And I'm going to do the same thing, observed minus expected squared for the non-variant covers. So I have 15 minus 20. I observed 15, I expected 20, I divide by 20. This is going to end up being 5 squared, or 25 over 20. And if you're like, well, hold up, isn't that a -5? That's the great thing about squaring it. It's causing everything to be positive on the top there. That's the reason why I do it. On this next one, I observe 185. I thought I should have gotten 180, so I'm off by a +5 this time. And I'm dividing that by 180. When I type this into my calculator, I'm going to do so now. I appear to get something like 1.388 repeating or so. So I have my first couple steps looking pretty good. I'm going to move on to my third step, p-value. It's right-tail test, so I'm going to have chi-squared CDF, the value I just came up with, comma infinity, comma my degree of freedom for this problem is 1. So I have 1.388 here. I'm going to type this into my calculator. I'm doing second vars, chi-squared CDF, 1.388 repeating, infinity, degree of freedom of 1, and I get, up to a little bit of rounding, 0.386. So, okay, looks like I have a large p-value. And if I have a p-value that is larger than, let's say, an alpha level of 5%, I fail to reject the null hypothesis. So I do not have evidence that Marvel's claim is unfair. So this tells me that the distribution that they're telling me could be a good fit. I don't have evidence that it's not a good fit. Now, if you're comparing this to what we did before, and I will move the page down here in just a second, I just want to see how things match up and kind of where they don't match up. One thing I'm noticing, p-value 2386, p-value 2386, that's looking pretty good. Other observation, -1.1 to a +1.388 repeating. I'm kind of curious what that relationship is. I'm noticing that I squared everything to get rid of the sign, so I'm a little bit curious what happens if I square this z-score. So this is just a guess. I don't know if this is actually going to prove useful or anything, but I'm taking this -1.1785 value, and I'm going to square it just to see what I end up getting. And that's a bit hard to see, but when I took this -1.1785 squared number, I ended up getting 1.388 repeating. So I ended up getting this chi-squared value that I had before. So here's an interesting observation, I think, is that if I take my z-scores and square them under the right conditions, when I'm allowed to do the same test for both of these things, I end up getting the chi-squared value. So when I'm saying stuff like the square roots of entries act like z-scores, I really mean that. They act a lot like z-scores. The z-scores and chi-squared values have this nice relationship between them. And this gives me a way to kind of double check my work. So most problems that I could do a hypothesis test for proportions, I should be able to redo that same thing using this chi-squared test. Now, I want to open up the door a little bit for other types of tests that I can do using chi-squared, because other things that I could use this z for, well, I also use z when I was comparing two proportions. So I'm wondering if I could just make like a grid of values and compare everything in the grid. In order to do that, I just want to practice some skills from an earlier stats course to make sure I'm comfortable with that stuff before moving onwards. So I'm reviewing the term of independence from a 243 course. And I say two random events, A and B, are considered to be independent if, this is the big one, if the outcome of event A does not affect the outcome of event B there. So if the two things do not affect each other, then I say they're independent. They're independent if the outcome of A does not depend on the outcome of B. So B can happen or not happen, the probability stays the same. So these are a little bit verbose. What this means in practice when you're looking at table is it doesn't matter if I'm looking out of the total, it doesn't matter if I'm looking out of the part of the table where B exists, or the part of the table where B does not exist. The proportion of A stays the same. So columns and rows, if it's independent, should be proportional. They should have the same ratio. So let's look at an example and determine if it's independent. Cat adoption team in Sherwood has 60 cats. So in total, I'm going to add totals to the outside of this two-way contingency table. And they're telling me it is out of 60, so I'm going to put that in the corner there. 20 are kittens. So if 20 are kittens, that must tell me that 40 are not kittens. It says 24 are male, so I'm going to put 24 for male. If 24 are male, this must tell me that 36 are not male. And it says 10 are male kittens. So any sort of compound events when I'm making these tables go on the inside. So any sort of and, male and kitten, those are on the insides of these tables. Any event that's just by itself, like just the word kitten, I'll call these things solo events. These show up on the outside. Let's fill in the rest of the table based off of this 10. So I'm wondering how many things do I need to know in order to fill in this whole grid? So I started with a 2x2 grid. And when I'm listing these things out for the dimensions, the first number I'm writing out is the row. Rows are like when you row a boat. You row a boat side to side. So rows, I have kitten and non-kitten, 2 rows. Columns are the next number. Like columns of a building go up and down. I have 2 columns, male and not male. So I started with a 2x2 grid or matrix. And I'm wondering how many of these inside boxes did I need to know in order to fill in everything? And so far, I just have 1 box, but let's see what I can solve, assuming I have the totals on the outside. 10 and 10 gives me 20, so I didn't need that box. I could solve for it. 10 and 14 gives me 24. I didn't need that. And last one here, 10 and 26 yields 36. Quick verify. 14 and 26 yields 40. That looks good. So in order to solve this entire starting grid, I only needed one of those initial values. So it looks like I have a df of 1 there. Now the big question was, is this independent or is this dependent? Well, let's look at the ratios. So here's what I mean by ratio. I should be able to take one of the columns, multiply it by something, and then get the same thing in another column. I usually do the first value as an indicator to see what I should be multiplying by. So to get from 10 to 10, I would have to multiply here by just 1. So if it was independent, I would have to do 14 times 1. I would get that same number here if it was independent, 14. I don't, I get 26. If I did 24 times 1, I should get 36. And I see that this ratio is not working. So it's not just multiplication by 1 the whole way across. It's a different ratio throughout. So since the ratio is not the same, the events could be or appear to be dependent. Now, I don't know if I'm off by a lot or a little, so here I was dead on for the first one for the ratio, fine. For the second one, I appear to be off by 12. That's a considerable amount of error. Next one, I'm also off by 12. I don't know percentage-wise if this is enough to make this thing have statistical evidence of a for sure dependency, but it certainly doesn't look great. Let's try another example of this ratio test just to see exactly what I mean by same ratio. So I'm going to take this first thing in A, and I'm just wondering, what do I need to multiply to get to the second column? And I'm going to wonder, is it the same thing to multiply the whole way through the grid? Well, to get from 3 to 12, I would have to multiply by 4. Well, to get from 13 to 52, I'm going to try doing 13 times 4, and I get 52. That's looking pretty good. I'm going to do 16 times 4. I get 64. That looks great. So when I get something like this, when I can multiply the whole way down and it's the same multiplier, this is what it looks like if it's independent. Dependent, I get different multipliers going across. Independent, it's the same. And the neat part is I should be able to take any two columns and do this. So for example, 3 to 15, that's multiplication by 5. If I do 13 times 5, I get 65. If I do 16 times 5, I get 80. So this appears to be independent. The ratios are the same. So this is going to be the big trick, is that if I want to make something be independent, I have to try to keep those ratios the same the whole way through the table. I'm going to do something a little bit different on this next one. This one's almost like working backwards. I just really want to make sure I understand this concept of independence, because ultimately today I want to be able to test if there's a relationship between two variables, and I just want to know what to look out for if there is or is not a relationship. So assume this table is independent. So this is telling me that the ratios are the same. Okay, so if the ratios are the same, let's think about what that would mean. Well, to get from 20 to 100, I would have to multiply this column by 5 to get here. Or another way of doing this was I would have to take this column to go this direction, and I would have to divide everything by 5 to go down. Let's see if that works. 100 divided by 5 is 20. Great. I'm going to try doing another one of these things. I have 75 divided by 5. I'm typing that into my calculator. I got 15. Oh, and I can use addition to kind of come up with the rest here. So I have a 2 by 2 grid. And I have one value so far. Let's see how much more I need to get the rest, because I only used a multiplication trick for one of these inside values so far. But 5 and 15 gives me 20. 5 and 20 yields 25. 20 and 60 yields 80. 15 and 60 yields 75. So it looks like I only needed to know one of those values for that 2 by 2 grid. I needed to know one of the row values and one of the column values, a 1 by 1 space. Let's check the rest to see if the ratios stay the same though. 5 to 25, that's multiplication by 5. 15 to 75, multiplication by 5. 20 to 100, multiplication by 5. Checking here, 5 to 20, I'm multiplying by 4 the whole way down. This table's looking pretty good. My ratios appear to be the same. Now, previously when we were working with chi-squared, we had the expected value was the number of values in total for something times the probability of that event. I want to use that to see if I can come up with this 15 number here. So let's see what's going on. The total for this was 75. And if I'm wondering, well, how much of this 75 should live here? That's what my ratio was telling me. And my ratio was this 20 out of 100 number. 20 out of 100 written a little bit differently. I was looking at 1/5 of 75 to come up with that number 15. This might be strange for a little bit, but I promise you that there's a reason for this madness here. I'm going to write this just a tiny bit different, because I just want to identify where all of these pieces are coming from, so I could come up with a formula that just gives me these values in general. So my expected value of this spot right here, I had the 75. That was the total for the row. And I multiplied it by 20. That was the total for the column. And I was dividing by 100. That was this number in the bottom right corner. That was the overall total. So I'm going to try this out here and see if this actually works. So let's look at the expected value of the spot where A meets B. That's this top left square. So I'm going to take the total for A. So I'm going down from A, and A happened 20 times. I'm going to look at the total of B. The total of B, 25. So I have the total of the row, I have the total of the column. I could list these in the other order, I'd still get the same value. Multiplication, I can switch the order. Divided by the overall total was 100. Let me try typing this into a calculator and seeing what we get. 20 times 25 divided by 100. I get 5. I was supposed to get 5. That's looking pretty good. Let's try doing another one. I'm going to put a little star by this one right here. Let's try to find that star value using this process. So I'm looking at the expected value of not A, but it is in B. So I am going to take the total for not A. Total for not A is 80 there. The total for B, that's 25. And I'm going to try dividing this by the overall total in the corner. So what I appear to be doing here is it looks like I am just taking the outside totals and I'm multiplying them, and I am dividing by the number that I have in the lower right hand corner. Let's give it a go. 80 times 25 over 100. This gives me 20 as I was hoping. This looks great. So to find the expected values, I can take the row total times the column total divided by the overall total. This keeps the ratios the same. I'm going to add one more thing to our toolbox here because I'm wondering how lazy I can be when I'm checking for independence. In this last one, it looked like I only had to use this multiplication trick really just once here because the rest I could solve using addition and subtraction. Well, let's see what's going on if I'm looking at different size grids. So for example, let's look at a 2 by 3 grid here. So 2 rows, B1 and B2, 3 columns, first A, second A, third A. And let's suppose I have the totals. Totals aren't counting as combinations of events. Totals, I am assuming, are given to me. Because the actual data is here. This is just the combinations, the totals on the outside. So if I have this 2 by 2 grid and I'm wondering, well, how many of these values do I need to know on the inside? Assuming nothing about being independent or dependent, I don't know what any of these numbers are. So I'm going to try dropping down one of the values and seeing what happens. Let's suppose this is a 5 here. If that's a 5, I can immediately solve for this bottom row value. So I only need to know the top row and I can solve for the bottom row. That's kind of a nice thing to know. But I don't have enough to solve for the rest of the columns. Let's get another value. Let's suppose this is 0. Well, if this is 0, 0 and 20 yields 20. I can solve for the bottom row, assuming I know the top. Well, I now know the two outside columns here. Let's see if I can find the final column. 5 and 0, I'm at 5 so far. I need 5 more to hit 10. I'm going to write this as 2 lines, so it kind of looks like an equal sign. 5 and 25 yields 30. 5, 25, 25, and 25 yields 50. So this is looking pretty good. So it looks like I had to know the top row and the inside columns there. So I could solve for one of the rows. If I had 2, I could get away with just one of them. And for the columns, if I had 3, I need to know 2 of them. So in total, it appears that I needed to know 2 of those values there, these 2 values, in order to solve for everything. Let's try another one. This one's going to be a 3 by 3. So I have first column, second column, third column, first row, second row, third row. And let's suppose I have 90 values, 20, 30, 40. I'm just making up these outside numbers. We are assuming nothing about independence here. And I'm wondering how much of this 3 row, 3 column grid will I need to know in order to know everything. Well, currently I can't solve for any of the values, so I'm going to add a 0 and see if that helps me. Because previously just one value allowed me to solve for something, and I'm going to see if I can solve for anything. Nope, too many unknowns in every direction. I can't solve yet. I'm going to give you another value. Let's assume this is 0. If this is 0 and 0 and this adds up to 20, this tells me this missing value here must be a 20. So for these 3 rows, it looks like I need to know 2 of the 3 rows. So for the rows, it appears as though I need all but 1. Let's see what's going on with the columns. 0, I can't solve for that 10. Let's suppose I have another number and that this ends up being 0. 0 and 0, that gives me 10 as my missing category there. Great. So it looks like for the columns here, if I have 3 columns, I need to know all but the outside one in order to solve for everything. So let's keep this going. So I can't solve this or this, so I'm going to add one more number. And let's see what we can find now. I'm at 0 so far, so I need one more number there, 30. I'm at 0 so far, so I must have 20 there. And this final number should work vertically and horizontally. 10 and 20, I'm at 30. 10 more gets me to my 40 as desired. 10, 40, 60 horizontally. This looks pretty good. I want you to notice that I solved everything except for, I needed everything except for this bottom row and this outside column. So I had to know this inside 2 by 2 grid. I needed to know 4 things. In general, it's going to work like this, where I need to know all of the rows but 1 and all of the columns but 1. So it's like I'm taking my previous degrees of freedom calculation and I'm multiplying them together when I have a grid. I have the degree of freedom for the rows times the degree of freedom for the columns. So for example, if I have 12 rows and 11 columns in a grid, then my degree of freedom, I would have to have degree of freedom for the rows, 11, degrees of freedom for the column, 10. I would need 11 times 10. I would need 110 squares in order to know everything. So my degree of freedom, I'm calculating this thing as R1 minus times C minus 1. And for my expected value, I have row times column over total. I'm going to write those observations again here at the top. Degrees of freedom, number of rows minus 1 times number of columns minus 1. If I want the expected value for some sort of a grid, I'm taking the total of the row times the total of the column divided by the grand total. Now I'm going to put a lot of things together on this next page. I'm actually going to look at a hypothesis test from start to finish. And I'm back to this cat adoption team in Sherwood problem that had 60 cats. I started with a 2 by 2 grid. So for degree of freedom, I'm going to have 2 minus 1 for the rows and 2 minus 1 for the columns. That's 1 times 1. I believe I'm going to have a degree of freedom of 1. What this means is I'm only going to have to use this multiplication trick to come up with one of the values for a table like this. So let's fill in our observed table here for what they're telling me. They said this was out of 60 cats. They said 24 were males, so that means 36 were not. 20 were kittens, so 40 were not. And they gave me one of the inside values. They said the number of male kittens was 10. Solving for the rest of these numbers, 10 and 10 gives me 20. 10 and 26 yields 36. 10 and 14 gives me 24. And 14 and 26 gives me 40. So I needed to know only one value to get that whole grid based off that information that we observed. And the question here is, are the events of male and kitten independent? So out of curiosity, I'm just going to create a what if grid down here. What if they were independent? What would I expect to see for a same kind of setup, assuming I actually had the ratios stay the same instead of change throughout the table? Well, let's look. I have 60. I have 24. I'm assuming that I still have the same totals. I'm just worried about keeping the ratios the same. And let me find one of these expected values. Let's find the expected number of male and kitten. So I'm finding this square right here. So what I'm going to do is I'm going to take the total for male. I'm just going to go from the spot in my grid, and I'm going to go down and over. I'm going to multiply these outside numbers together. So total for male, 24. Total for kitten, 20. And I want to divide this by that gram total that I have in the bottom right corner. I want to divide this by 60. I'm going to type this into my calculator and see what I get. Now I might end up getting a decimal. That would be totally okay to end up with the decimal here, because the expected is kind of something that's happening on average. Sometimes it'll be higher, sometimes it'll be lower. I don't get a decimal. I get something pretty nice. I just get 8. So now I was expecting 8 if it was independent. I got 10. Looks like I'm off by 2 animals there. That doesn't feel like a ton of error, so let's keep going. 8 and 16 yields 24. 8 and 12 gives me 20. 12 and 24 gives me 36. 16 and 24 gives me 40. This is looking pretty good. So now when I compare these two tables, it looks like I'm off by 2 in a lot of these categories. So what previously looked like a ton of error, when I'm actually considering the ratios a bit more carefully, I'm not sure if I'm off by that much. In fact, let's try to test this using a hypothesis test. I'm going to remember what the 4 steps of a hypothesis test are. First step, I have my hypotheses. Second step, I want to kind of compare this, what I'm seeing, to what it would actually look like if it was independent. So I want to compare counts. So there should be some model that allows me to compare counts. I'm going to calculate a p-value, and I will determine my conclusion after I calculate that p-value. So I'm using the same 4-step process on every test throughout this course. So null hypothesis. Well, let's just set this up as null hypothesis. The events are independent. In other words, being a kitten does not affect the probability of being male. For the alternative hypothesis, let's test if they are not independent. In other words, let's see if there's a dependency between these variables. So for model, I want to compare the independent case to the actual case to see how close these are. So I'm going to be comparing my observed values to my expected values. Well, I already have a model that does this. I have chi-squared. It takes all of the observed values and it compares them directly to the expected values by doing observed minus expected squared over expected. So I'm going to do that for this grid here, and I just want to match things up as I go along. So for example, for male kittens, and I like to put light dashes through them as I'm kind of matching them up, there was 10 there. I was expecting 8. Squared over, I was expecting 8. So I can see my error of 2 for that first category. Let's look at the next category. I have non-males, 10, and I thought there should have been 12. Squared over, I thought there should have been 12. Plus, and I could do this plus as just like a big plus sign that goes on. I'm writing it as a grid so I can see the values a little bit better. Next value, 14, minus, I thought it should have been 16. I thought it should have been 16. Last one, it looks like I have 26 minus, I thought it should have been 24 squared. I thought it should have been 24. And if you're thinking, well, shouldn't I take these outside numbers too? Well, let's just see what happens if I do that. 20 minus 20 gives me 0, so I would end up with nothing that I'm adding for that. 40 minus 40 is 0, so all these outside values, those are going to match up perfectly every single time. They are not going to contribute to this chi-squared number. So I'm going to type this into my calculator and see what I get. And I appear to get a chi-squared of 1.25. So I have my hypotheses. My null hypothesis is always going to be independent. This assumes there is no relationship. Alternative hypothesis, I'm testing if there's a relationship. For the model, it's chi-squared. I'm comparing the counts. For the p-value, it's always a right-tailed test. So it's going to be chi-squared CDF, whatever my chi-squared number is, comma infinity, comma whatever my degrees of freedom happen to be. In this case, my chi-squared number was at 1.25 value, and my degree of freedom was 1. When I type this into my calculator, I end up getting a p-value of approximately 26.4%, which is pretty large, all things considered. Since my p-value is bigger than a neutral alpha level of something like 5%, I would fail to reject the null hypothesis. So I do not have evidence of a statistically significant relationship, read as being dependency, between gender and being a kid. So it's not like this facility is just hoarding up on only male kittens and they don't have that many non-male kittens. There appears to be no relationship between these things when they're pulling them in. These two variables do not have a statistically significant difference. So if I were to calculate these standardized residuals as I'm going along, I should probably end up with a whole bunch of values here that are not unusual. Standardized residuals, I'm taking the observed value minus the expected over the square root of expected. And let's try doing this for the male kitten category just to verify that it's business as usual for each of these things. So for male kitten, I observed 10. I thought I should have gotten 8. I thought I should have gotten 8. So it's just the square root of one of those entries. When I do this, I get approximately 0.707 or so. This is within 2 standard deviations. It appears to be usual. So the thing that I found kind of interesting is as soon as I could come up with this table where I kept the ratios the same, as soon as I had something to compare to, these tests end up being fairly quick. They might be labor intensive at times, but they're fairly quick, all things considered. I want to try to do this for another scenario just to see exactly how useful chi-squared is, but I can already compare the success rate for 2 groups in a way that I used to use 2 proportions for. So just a little bit of vocab. The same process can be used to see if 2 variables are related. That's what we just did. I'm testing for independence. I can also check to see if the ratios are the same for multiple columns. If I'm seeing if the distribution is the same for a whole bunch of groups, that's called homogeneity. Homo meaning same, geneity throughout. So are these distributions the same throughout? As an example of this, let's check a test for goodness of fit, where I'm comparing one variable in one distribution to a claimed distribution. A test of independence compares two or more variables to see if they're related. And this is an important thing to note. The way that I tell these things apart is by where the data is coming from. So independence, the data comes from one large sample, and then it is sorted accordingly. For homogeneity, this comes as several subpopulations. So this is collected separately for homogeneity. Independence, it's typically collected all at once. So let's look at these scenarios and see if we can figure out what type of test they are. We want to see if there's a relationship. Well, first off, I see the word relationship. This makes me think that maybe this could be a test for independence between gender and healthcare. Well, I could ask someone those two things at the same time. What do you identify as for your gender, and do you have healthcare? Since I can ask this all at once as one big sample, this is sounding like independence. It's testing for a relationship. That's two reasons why I would say this is a chi-squared test for independence. Division Dean wants to compare the final grade distribution for 3 different professors to see if they look the same. The word same is a cue. If I'm trying to see if different things look the same, usually this is telling me something about homogeneity. Let's look for another cue. I'm collecting the data from 3 different spots. So I collected all for the first professor, then I have to go somewhere else and collect it all for the second professor, and then I have to go somewhere else yet again and collect it all for the third. So I see several small samples happening here. This is verifying for me that this appears to be homogeneity. So there are kind of 2 things to cue you into what's going on. First off, if I'm testing for sameness, that's homogeneity. If I'm testing for a relationship, that's independence. But it's also how the data is collected. Laura at OHSU wants to check if there's a relationship. This is going to be independence. A test for independence. And blood pressure and having diabetes, I can ask them both questions at the same time. I'm getting all that information at once. That feels like independence. Trading card company claims that 5% of cards are rare, 20% are uncommon, and 75% are common. We want to test the claim. Well, here I'm given a whole bunch of numbers, and I want to know if these numbers fit my data or do not fit my data. So this sounds to me like a goodness of fit test. This gets abbreviated sometimes as GOF. If you see that, that's what that means, goodness of fit. Let's look at one of these and figure out exactly what that test would look like from start to finish. Wants to compare the distribution for 2 different instructors, and I'm asked, do the distributions appear the same for these instructors? So this sounds like a test for homogeneity. When I'm doing a test for homogeneity, my null hypothesis would be that there's no relationship between the 2 groups. In other words, that there wouldn't be anything that's kind of changing between those grade sets. It's not like Mr. Wary passes a significantly more number than Mrs. Mache there. I just want to compare them up and see what's going on. So null hypothesis would be that things kind of look the same, that there's nothing weird that's happening, homogeneity. Alternative hypothesis would be that they do not look the same. So null hypothesis will always be something about sameness. Grades look the same for the 2 instructors. Alternative hypothesis, not the same distribution for Wary and Mache. So I have my first step there. Let's look at the second step and think about the model. I can count how many people passed, failed, and withdrew from the class. So I have countable data. And if it's countable data, that tells me for the model, I'm going to be using this chi-squared. Chi-squared will compare observed data with expected data. So I should have two different grids here that I can compare side by side. Let's start with the observed. I have information for wary. I'll use WH for wary. And I have information from Mouchet. I'll use M for that. For the columns, I have students that pass, I have students that withdraw, and I have students that fail. On the outside, I have my totals, and I'll figure out my totals as I'm going through the problem. So wary passed 50. I had 20 that failed, and I had 10 that withdrew. 50, 10, 20, and 80 total there. For Mouchet, passed 80, total of 130. Withdrew 30, total 40. Failed 10, total 30. And in total, looks like they had 120 students. Adding everything up together, that gives me a grand total of 200 people between these two instructors. Now, what I'm going to do for testing for sameness is I want to keep the same number of students in each of these categories, but I want to have things be more even or fair throughout. So I'm hoping that I kind of have the same ratios. If I have 80 students out of 200 here, whatever proportion that is, I'm hoping that I have the same proportion for pass and withdraw and for fail, that I keep the ratios the same. So for expected, and I'm going to find the expected by taking the total of the row times the total of the column divided by the overall total. Let's see what that looks like. And I'm keeping these outside numbers the same, 80, 120, 200. Nothing's changing there. 130, 40, 30. I'm going to start with the expected number of students that should be in this top left category, wary and pass. So I'll take the total for wary. There are 80 people there. I'll take the total for pass. There is 130 people there. So I'm multiplying these numbers on the outside. And the nice thing about multiplication is I can do them in either order, so do whatever's convenient. And I'm going to divide this by that overall total of 200. 80 times 130 over 200. I was expecting to get a decimal because there's messy numbers, but I actually ended up getting a little bit lucky again. This is a whole number. That's 52. I like that. Let's find another one of the expecteds. Let's find this one for wary and withdraws. So I'm going to take the numbers on the outside. So straight down and straight across, I have 40 and 80. Wary, withdraw. And I'm going to divide this by the overall total. The overall total is 200. I'm going to type this into my calculator yet again. When I do this, I appear to get 16. If you're following along at home, I'm going to ask that you pause the video and try to do the rest of the table here. Now, just as a trick, I have a lot of these values already, so I might be able to get the rest just using addition and subtraction, or keep using this multiplication formula to figure out those values. Go ahead and pause the video, see what you can come up with. I'm going to use my addition trick here. 52, and I had 78 for this value here. 16 and 24 for this value here. I am at 68, so I needed 12 more here. 12 and 18 yields 30. I have 18 in that column right there. So in order to solve for this entire 2x3 grid, it looks like I needed to know these two values. So another trick for coming up with this degree of freedom is you can just cover the outside column and the outside row of your grid that you're solving for and count the number of squares. That's your degree of freedom. And I just want to take a quick glance at this to see if it's close or not close. 52 and 50, that's pretty close. Oh, that's off by 6. I'm not feeling great about that. Off by 8, off by 8, off by 6, off by 2. So some of these look really close. Other things, this withdrawn failure rate, these look a little bit more off, so I might have some error there. So let's calculate our chi-squared value to see what's going on. And I'm going to start by taking an observed value 50 minus the corresponded expected value 52. I'm going to square it. And I'm going to divide this by that expected. I'm going to add this up for everything in my grid here, and we'll see what we get. If you're following at home, pause the video, give this a go. I'm going to do it as well, but try it out and see what you get. I'm going to do matchy-matchy. 50 matches up with 52. The expected is 52. Plus dot, dot, dot. 10 minus 16 squared divided by 16. 20 minus 12 squared divided by 12. 80 minus 78 squared over 78. 30 minus 24 squared divided by 24. 10 minus 18 squared divided by 18. I just match them up and I add them all together. When I do this, I appear to get a chi-squared value of approximately 12.767. So first step, hypothesis. Second step, I make these grids. And the grid was exactly the same when I tested for independence. So the math doesn't change. It's just some of the wording. Third step, I'm going to calculate the p-value. It's a right-tailed test, so I'm going to do chi-squared CDF. I'm going to start this thing at 12.767, comma, infinity. It is a right-tailed test, comma, my degree of freedom here was 2. When I type in this chi-squared into my calculator, go ahead and do that, see what you get. I appear to get 0.0017. I would say this is a fairly small p-value. So when I'm in this conclusion step and I'm wondering, should I reject or fail to reject? In this situation, I might compare to an alpha of, say, 5%. If my p-value is low, I might reject the null hypothesis. If the p-value is low, the null must go. If I'm rejecting the null hypothesis, this must mean I have evidence of a difference. So this tells me I have evidence that the grade distributions are not the same. So this tells me that these two instructors are not grading consistently, or they're not getting the same kind of student groups to do so in the first place. But this doesn't really tell me why the grade distributions are different, and it also doesn't tell me how they're different. If I wanted to try to figure out which one of these things are a little bit abnormal, I should follow this up by finding each of those standardized residuals to figure exactly where all of these things are different. I want to do just one or two more quick problems with you here. I'm looking at the final page of this particular packet. And I'm going to do the same problem in two different ways, just side by side, so you can see what this looks like. Test the claim that the probability of winning a contest by Coca-Cola is 1 in 4 if we actually win 10 in 60 trials. Do this once using goodness of fit and once using one proportion. So this is a lot like that first problem that we warmed up with in this packet. So using the chi-squared method, they tell me that I should win the contest 1/4 of the time. If I'm winning 1/4 of the time, this means I'm losing 3/4 of the time. If the thing they're telling me is not fair, then at least one proportion would be different. Second step, model. I'm going to determine the observed values for wins and losses. And this one I don't need a Mondo grid like the last couple of problems, because I can actually just see from the statement they played 60 times, they won 10 times, so they must have lost 50. But I'll have to compare this to what I was expecting to get. Because chi-squared always does the same thing where it compares expected and observed. Whether it be from a list of values or a grid from values, it's always expected and observed that I'm comparing. While this should still be out of 60 trials, but 1/4 of 60 is 15. So I got this by doing 1/4 of 60. If I should win 15 times, I'm off by 5. I should lose 45 times. I'm going to calculate my chi-squared by taking the first observed value, 10, minus the expected, 15, squared over the expected. Next value, 50 minus the expected, 45, divided by the expected, 45. I'm going to type this into a calculator and see what I get. And I appear to get a chi-squared of 2.2 repeating. Third step, p-value. Chi-squared CDF. This is a right-tailed test, so 2.22 to infinity. And in order to fill in each one of these small little grids, I needed to know one of the two values to solve for the rest. So my degree of freedom was this k minus 1. In this case, I only needed to know one of those values. This gave me a p-value of 13.6%. Conclusion, my p-value is bigger than an alpha of 5%, so I fail to reject the null hypothesis. I have no reason or evidence to believe Coca-Cola's claim is not fair. Let's do the same thing now with the z-test and see how stuff matches up. So previously, I did this using just one letter p. The proportion I was claimed was 1/4 for my win rate. So I only need a single proportion here when I'm working with a one prop z test. And I'm testing to see if it's different. Step 2, I'll come up with my model. P hat is normally distributed with the center of P, and the standard deviation of root PQ over N. I have 25%, that's 1 out of 4 as a decimal, is 25%, will be my center. My failure rate is 75. I still have that 25 and 75 showing up as part of the model. And this was done for 60 trials. When I type this into my calculator, I end up getting a standard deviation of about 0.0559 or so. My model over here, much cleaner. I didn't need a square root. I could have actually done this thing by hand for the most part. So far this appears to be sort of a cleaner way, even though this might have a couple less steps. Third step, p-value. And I'm going to look at the likelihood of my sample data or more extreme. So not equals. This is going to be a two-tailed test. My center is 25%. My sample success rate was 10 out of 6 as a decimal. That's 0.166 repeating. And I'm going to shade both left and right. This is a two-tailed test. So for my z-score, I have 0.166 repeating minus 0.25 divided by my standard deviation of 0.0559, and I get for one of my z-scores negative 1.49. Just as a quick check, if I take this negative 1.49 value and square it, I end up getting 2.22 repeating. So again, my observation, if I take my z-scores and I square them, they should match up with the chi-squared value if you're analyzing the same data set in two different ways. I'm going to look this z-score up in a table. When I do so, it tells me that the area in this left tail is 0.068 or so. Great. I have a two-tailed test, so my p-value is going to be 2 times that area to the left. When I do 2 times this, I get something of about 0.136 or so. So interesting enough, I end up getting exactly the same p-value, which means I have exactly the same conclusion. I failed to reject the null hypothesis. I have no evidence to believe that Coca-Cola's claim is not fair. What I would challenge you to do is do another problem here, once with chi-squared and once with a different model 2-proportion z-test. When you're doing this 2-proportion z-test, you had to use a trick of pooling. Well, I don't have to pool anymore when I'm working with chi-squared. It kind of does that for me naturally. And I want you to see which one of these processes you think is easier. I tend to think that chi-squared gives you cleaner numbers and cleaner math, less square roots, less messy decimals. But use a method that you're ultimately going to be the most comfortable with. We've now looked at 1 proportion, 2, 3, or however many proportions you want to compare. We've dealt with confidence intervals for 1 proportion and 2 proportions. We've looked at 1 average. We've looked at matched paired averages. We've not yet looked at 3 or 4 averages in the same way that chi-squared looks at 3 or 4 proportions. So next lesson, lesson 12, is going to look at an analysis of variation where it compares all the averages for multiple groups. And we're going to see a lot of similarities to what we've been doing here with this chi-squared model. So we'll see things like right-tailed tests still show up. I'll be comparing some sorts of variations between 2 groups. And I'll have something going on with degree of freedom. So lesson 12, it's going to be a 2-part lesson. It's on analysis of variation, and it's on comparing averages.